Now that we have discussed the basic concepts, idea, and need for pre-stressed concrete, we are now presented with the first assignment of this course, that is assignment number 1, based on the fundamentals of pre-stressed concrete. That is assigned with the objective of illustrating the basic concepts, idea, and need of pre-stressed concrete in the presence of reinforced concrete that was already established as a successful building material by the 1920s, that is the early 20th century, when pre-stressed concrete was first introduced as an alternative, superior construction material in comparison to reinforced concrete. As you may note from the question statement of question number 1 in assignment number 1 for this course based on pre-stressed concrete and industrial structures, with the assignment number 1 focusing on the fundamentals of pre-stressed concrete. A pre-stressed concrete bar with a prismatic rectangular cross-section of dimensions width B and depth D and overall length L is composed of M40 grade concrete and is pre-stressed with high tensile pre-stressing steel of area A subscript S in the form of a high tensile pre-stressing steel bar located concentrically at the centroid of the cross-section, that is a concentric pre-stressing steel bar of area A subscript S and the pre-stressed concrete bar thus constituted is subjected to an externally applied concentric axial tensile force capital T. Given the question statement, we are required to solve the questions 1A, 1B, and 1C for the prismatic pre-stressed concrete bar with a rectangular cross-section of dimensions consisting of width B and depth D, that is the gross area of the cross-section as B times D, with an overall length denoted as capital L, composed of M40 grade concrete and pre-stressed using a concentric pre-stressing steel bar of steel area A subscript S, that is located concentrically at the centroid of the cross section of the pre-stressed concrete bar, detailed above. On the application of an externally applied concentric axial tensile force denoted as T. Well, the best and the most effective manner to illustrate the methodology for the solution to question number 1, parts A, B, and C of assignment number 1 displayed on the present slide is to refer to a solved example that is an illustrative example to explain the methodology for the solution of question number 1 of assignment number 1 presented on the current slide. And therefore, we will proceed to the illustrative example, that is solved example for illustrating the guidelines for solving the question number 1 of assignment number 1 in this present course. In the next slide, that presents a detailed solved example with elaborate guidelines for solving question number 1 of assignment number 1 of the present course. As mentioned earlier, the most effective and efficient approach for illustrating the detailed guidelines for the solution of question number 1 of assignment number 1 presented in the previous slide is to solve an illustrative example of a identical pre-stressed concrete bar that is prismatic with a rectangular cross-section composed of M40 grade concrete, wherein we are required to first calculate the design value of the pre-stress denoted as sigma subscript Cp that is required to ensure that the pre-stressed concrete bar that is provided with 0.4% of high tensile pre-stressing steel by area, that is the percentage steel, so steel ratio is defined as the ratio of the pre-stressing steel area to the gross concrete area, with the yield stress of the pre-stressing steel given as sigma subscript SPY, where the subscript S denotes steel, the subscript P denotes pre-stressing steel, while the subscript Y denotes the yield stress. specified as 1660 MPa. As given in the question statement of the solved example, and the design value of the pre-stressed concrete, denoted as sigma Cp, where the subscript C signifies concrete, while the subscript P signifies that the pre-stress is due to the pre-stressing steel, should be of such a magnitude such that the concrete in the pre-stressed concrete bar remains uncracked in a working stress range, that is the range of externally applied average tensile stress corresponding to the range of working loads or the range of service loads, that is working load given as 0 to 7 MPa, as opposed to the working stress range for the range of working loads given in the assignment question number 1 of assignment number 1 as 0 to 6 MPa, the corresponding working stress range or the range of externally applied average tensile stress under working loads or service loads given in the solved example is 0 to 7 MPa. A slight or a marginal difference. However, the difference will result in completely different results or the design value of the pre-stress sigma Cp in case of the solved example presented in the current slide with respect to the results of the question number 1 of assignment number 1 presented in the previous slide. Other than the difference in the working stress range or the range of externally applied average tensile stress for the working loads or service loads given in the solved example presented in the current slide, all the remaining data, that is the cracking stress of concrete, the modulus of elasticity of the pre-stressing steel, that is the Young's modulus, as well as the cracking strain of concrete have been given as the same values as specified in question number 1 of assignment number 1. That is, the cracking stress of concrete, or the cracking strength of concrete, or the modulus of rupture of concrete, denoted as sigma subscript CR, is 5% of the characteristic compressive strength, where the characteristic compressive strength of concrete is given as 40 MPa, corresponding to M40 grade concrete, which is the same grade of concrete that is specified in question number 1 of assignment number 1. While the modulus of elasticity of the pre-stressing steel, which is more or less a universal constant, has been given as 2 into 10 to the power 5 MPa. That is also the same as the modulus of elasticity of steel specified in question number 1 of assignment number 1. Further, the cracking strain, or the average applied tensile strain, epsilon CR, corresponding to the cracking stress sigma CR, is also given as the same as that specified for question number 1 of assignment number 1, that is cracking strain epsilon CR equal to 0.0002, that is 0.02%. Further, the yield strain corresponding to the yield stress specified in the solved example presented in the current slide can be readily calculated by dividing the yield stress sigma SPY by the modulus of elasticity of the pre-stressing steel, ES, therefore, based on the given data, for the prismatic, reinforced and pre-stressed concrete bar, each with a rectangular cross-section and each composed of M40 grade concrete of identical cross-sectional geometry, we are required in the present solved example, to compute and plot the uniaxial tensile stress strain response, first for the pre-stressed concrete bar up till the ultimate tensile strain given as epsilon Cu equal to 0.003, where the notation epsilon denotes strain while the subscript C signifies concrete and the subscript U signifies that the tensile strain is at the ultimate limit state or at the failure of the pre-stressed concrete bar due to the failure of the pre-stressing steel caused by the rupture of the pre-stressing steel. And then in part B of the solved example, we are required to compute and plot the uniaxial tensile stress strain response for the corresponding reinforced concrete bar, that is abbreviated as RC for reinforced concrete, and is provided with 1.6% of Fe415 high yield strength deformed steel, designated as HYST steel for high yield strength deformed steel. Given as the data for the corresponding reinforced concrete bar in the solved example. It is worthwhile to mention here that the data considered for the corresponding reinforced concrete bar that is also prismatic with an identical geometry, that is an identical rectangular cross section, and is composed of an identical grade of concrete, that is M40 grade concrete, as the pre-stressed concrete bar in part A of the solved example, is the same as the data provided or specified for the reinforced concrete bar of identical geometry and identical grade of concrete in question number 1 of assignment number 1. Therefore, it may be noted that the data on the cross-sectional geometry, material properties, that is the grade of concrete, and the ultimate as well as yield strength of steel including the ultimate tensile strains at the failure or the ultimate limit state of the bar due to rupture of the pre-stressing or reinforcing steel that is given in the present solved example is the same as that given or specified in question number 1 of assignment number 1. The only difference or exception is the working stress range or the range of an average applied tensile stress under working loads or surface loads for which the concrete is required to be uncracked. In other words, the only difference in the data provided in the solved example presented in the current slide with respect to question number 1 of assignment number 1 is the working stress range or the range of externally applied average tensile stress under working loads or service loads that is given as 0 to 7 MPa in case of this present solved example, while the working stress range specified in the question number 1 of assignment number 1 under which concrete is to remain uncracked has been specified as 0 to 6 MPa. Barring this minor difference in the working stress range or the range of externally applied average tensile stress under working loads or service loads for which the concrete is to remain uncracked, all other data that is given in this present solved example on the current slide is the same as that for the question number 1 of assignment number 1 presented in the previous slide. Additionally, there are two design parameters that are worthwhile to note. From the question statement of the solved example presented in the current slide, as well as the question statement of question number 1, assignment number 1, presented in the previous slide, and that is, it should be noted that the normalized steel ratio, denoted as rho n, where the notation rho denotes ratio of the steel, while the subscript n denotes that the ratio is normalized with respect to the material strengths of the constituent materials in the pre-stressed concrete bar or the reinforced concrete bar. One may note that the normalized steel ratio, denoted as rho n and defined as the product of area of the steel, AS, times the yield strength of steel, sigma SY, divided by the area of the gross concrete cross-section, denoted as AC, times the characteristic compressive strength of the constituent concrete material corresponding to the given grade of the concrete. Is the same in case of the reinforced concrete bar, defined in the solved example presented in the current slide as that or the normalized steel ratio of the pre-stressed concrete bar. Considered in part A of the solved example presented in the current slide. Since the yield strength of steel and the characteristic compressive strength of concrete considered for the reinforced concrete bar, specified in part B of the solved example presented in the current slide, are such that the normalized steel ratio, denoted as rho n, which is essentially the steel ratio by area, when normalized with respect to the strengths or yield stresses and characteristic compressive strengths of the steel and concrete respectively, work out to be the same as that for the pre-stressed concrete bar. Based on the given data for the pre-stressed concrete bar in part A of the present solved example. The verification of the equality between the normalized steel ratio of the reinforced concrete bar specified in part B of the present solved example based on the given data and the normalized steel ratio rho n of the pre-stressed concrete bar based on the data given for the pre-stressed concrete bar in part A of the present solved example is left to the reader as an exercise. The second design parameter that is to be noted before proceeding to the solution of the given illustrative example is that the external tensile force or externally applied tensile load, denoted as capital T, is applied after the completion of the pre-stressing operation. And therefore, the externally applied average tensile stress is measured upon the completion of the pre-stressing operation, that is at the end of the pre-stressing operation, increasing from 0 at the end of the pre-stressing operation to ascending values on the application of the externally applied tensile force or the externally applied tensile load T. While the average applied tensile strain, on the other hand, is measured prior to the pre-stressing operation, that is post-tensioning operation in case of a post-tension pre-stressed concrete bar. Since the strain gauges are installed on the pre-stressed concrete bar for purposes of measuring the average applied tensile strain, prior to the pre-stressing operation. And therefore, the state of stress and strain in the pre-stressed concrete bar upon the application of the externally applied tensile force or tensile load, denoted as capital T, is 0, 0. Prior to the pre-stressing operation. After the completion of the pre-stressing operation, the state of stress that is measured for the externally applied average tensile stress is 0, while the state of strain that is measured in the pre-stressed concrete bar after the completion of the pre-stressing operation is equal to or defined by the pre-strain. The pre-strain in the due to the pre-stressing steel that exists in the concrete of the pre-stressed concrete bar prior to the application of the externally applied tensile force or tensile load T. Therefore, the uniaxial tensile stress strain curve for the pre-stressed concrete bar that is measured and plotted subsequent to the pre-stressing operation, but from the point of application of the externally applied tensile force or tensile load, as the externally applied tensile force T increases from 0, is displayed with respect to the transferred coordinate axis or shifted, that is transferred frame of reference highlighted as coordinate axis x dash y dash, representing the origin or the 0 values of the state of stress and strain in the pre-stressed concrete bar after the post-tensioning or pre-stressing operation. Upon the application of the externally applied tensile force T. With that introduction to the design data and the design parameters given for the solved example, for the purposes of illustrating the detailed guidelines for the solution of question number 1 of assignment number 1, we will now proceed with the analysis and design calculations that are required for the solution of the uniaxial tensile stress strain behavior of the pre-stressed concrete bar and the corresponding reinforced concrete bar given in the solved example presented on the current slide. Therefore, proceeding to the solution of the illustrative numerical example presented in the previous slide, referred to as the solved example in the current slide, we will attempt to plot the uniaxial stress strain response of the pre-stressed concrete bar, for which the numerical data is given in the question statement of the illustrative example presented in the previous slide, as well as the uniaxial stress strain behavior of the corresponding reinforced concrete bar, that is the RC bar, for the purposes of comparing and contrasting the uniaxial tensile stress strain performance of the given pre-stressed concrete bar with reference to the reinforced concrete bar of identical geometry and grade of concrete as that of the corresponding pre-stressed concrete bar. Noting from the question statement of the illustrative numerical example presented in the previous slide, the cracking strain of concrete epsilon CR is given as 0.0002, that is 0.02%, while the cracking stress is specified as sigma CR, which is given as 5% of the characteristic compressive strength of the grade of concrete composing the pre-stressed concrete bar or the reinforced concrete bar, calculated as 2 MPa. Thus, the elastic modulus of concrete defined as the slope of the initial straight line portion or the elastic stress strain curve for the pre-stressed concrete bar or the corresponding reinforced concrete bar may be calculated as the ratio of the given cracking stress sigma CR to the given cracking strain epsilon CR, calculated as EC, the elastic modulus, of concrete equal to 10 to power 4 MPa. Further, the elastic modulus of steel, that is more or less a universal constant denoted as ES, has also been given in the question statement of the illustrative numerical example presented in the previous slide as 2 into 10 to power 5 MPa. The modular ratio, that is the ratio of the elastic moduli or elastic modulus of steel ES also known as the Young's modulus of steel, to the elastic modulus of the concrete for the grade of concrete composing the pre-stressed concrete bar or the corresponding reinforced concrete bar, can therefore be calculated as 20. The ratio of the pre-stressing steel by area, termed as the steel area ratio, for the pre-stressed concrete bar denoted as rho SP, where the notation rho signifies the steel area ratio, while the subscript S denotes steel and the subscript P signifies the pre-stressed concrete bar. That is, the steel area ratio is that for the pre-stressing steel in the pre-stressed concrete bar may be calculated as the ratio of the area of the pre-stressing steel ASP in the pre-stressed concrete bar to the gross area or the gross concrete section, thus calculated as 0.004 or 0.4%. The design range of working stresses, or the working stress range, under the working loads or service loads for which the concrete is required to remain uncracked in the pre-stressed concrete bar, has been specified as 0 to 7 MPa in the question statement of the illustrative numerical example presented in the previous slide. Hence, the design pre-strain, that is denoted as epsilon Cp, where the notation epsilon signifies strain while the subscript C denotes concrete and subscript P denotes the pre-stressed concrete bar or pre-stressed concrete, that is required to ensure that concrete remains uncracked in the given or specified working stress range under working loads or service loads from 0 to 7 MPa, may thus be calculated by dividing the difference in the maximum tensile stress specified as 7 MPa in the required working stress range of 0 to 7 MPa, and the inherent cracking strength or cracking stress of concrete, that is a material property of concrete, termed as the modulus of rupture of concrete, and is given as 2 MPa, or rather calculated as 2 MPa. Dividing the difference between the maximum tensile stress to be achieved for the desired or design range of working stress, that is 7 MPa minus the inherent cracking strength of concrete, that is 2 MPa, by the elastic modulus of concrete. One can calculate the design pre-strain that is to be induced in the pre-stressed concrete bar as minus 5 into 10 to the power minus 4. The minus sign signifies compressive or pre-compressive or pre-stress that will be required to ensure that concrete in the pre-stressed concrete bar remains uncracked in the specified working stress range of 0 to 7 MPa. Therefore, the design pre-stress denoted as sigma Cp that is the pre-compressive stress that is required to be induced in the concrete of the pre-stressed concrete bar by the pre-stressing steel, where the notation sigma denotes stress while the subscript C signifies that the stress is in concrete, while the subscript P signifies that the stress is due to the pre-stressing operation or the pre-stressing steel in the pre-stressed concrete bar can be related to the design pre-strain as the product of the elastic modulus of concrete to the design pre-strain, thus calculated as minus 5 MPa, where the minus sign is representative of the compressive nature of the pre-stress induced by the pre-stressing operation. Alternatively, the design pre-stress or pre-compressive stress that is required to be induced in the concrete of the pre-stressed concrete bar to ensure that concrete remains uncracked in the working stress range may be directly calculated by subtracting the inherent cracking strength of concrete computed as 2 MPa, that is the cracking stress or modulus of rupture of concrete, a material property of concrete, from the maximum tensile stress in the designs range of working stresses specified in the question statement of the illustrative numerical example presented in the previous slide as 0 to 7 MPa. Hence, the design pre-stress or the pre-compressive stress that needs to be induced in the concrete, in the pre-stressed concrete bar, prior to the application of the externally applied tensile force T may be simply obtained as 7 MPa minus 2 MPa, resulting in 5 MPa, and since the design pre-stress is compressive, the resulting value of 5 MPa is prefixed by a negative sign in this equation for the design or desired pre-stress or pre-compressive stress that will ensure that the concrete remains uncracked in the specified range of working stresses under the working loads or service loads given as 0 to 7 MPa. Continuing with the pre-processing of the design data provided in the illustrative numerical example presented in the previous slide, the ultimate tensile stress, also termed as the ultimate tensile strength or simply the tensile strength of the pre-stressing steel, may be calculated as the yield stress specified for the pre-stressing steel divided by 0.8, thus calculated as 2075 MPa. Since typically the yield strength or yield stress of steel in general is 80% or 0.8 of the ultimate tensile stress or the tensile strength of the steel. And therefore, applying the characteristic relationship between the yield stress of steel to the ultimate tensile stress or the tensile strength of steel illustrated in this relationship, one can estimate the ultimate tensile stress or tensile strength of the pre-stressing steel as the ratio of the yield stress, that is 1660 MPa to 0.8, thus computed as 2075 MPa, wherein 1660 MPa is the given yield stress or yield strength of the pre-stressing steel. Further, The yield strain, or the strain at which the pre-stressing steel yields, denoted as epsilon SPY, where the notation epsilon signifies strain, while the subscript S denotes steel, the subscript P denotes the pre-stressing steel, and the subscript Y signifies yielding, or the yields point of the pre-stressing steel, may be simply calculated as the ratio of the yield stress of the pre-stressing steel, denoted as sigma SPY, to the modulus of elasticity of steel, or the Young's modulus of steel. ES thus calculated as 1660 MPa divided by 2 into 10 to the power 5 MPa, resulting in a value of 8.3 into 10 to the power minus 3 for the yield strain of the pre-stressing steel, that is epsilon SPY. So with that basic design calculations for the material properties of the constituent materials, that is the pre-stressing steel and the concrete in the pre-stressed concrete bar, we will proceed to the derivation of the uniaxial stress strain curve of the pre-stressed concrete bar starting from the state of zero stress and zero strain, denoting the average applied tensile stress in concrete, calculated as the ratio of the externally applied tensile force T to the gross concrete area of the pre-stressed concrete bar as sigma C, that is the average applied tensile stress in concrete, and the average applied tensile strain as epsilon C, calculated simply as the ratio of the increase in length of the pre-stressed concrete bar to the original length under the action of the externally applied tensile force T, we will begin to trace and locate the path of the uniaxial stress strain curve for the pre-stressed concrete bar, beginning from the state of zero stress and zero strain, that is zero values for the applied average tensile stress sigma C in concrete, as well as the average applied tensile strain in concrete epsilon C. So beginning from the 0 values for sigma C and epsilon C, assuming that the strain gauges are installed on the pre-stressed concrete bar prior to the pre-stressing operation, that is prior to the pre-stressing of steel, and therefore the strain, average applied tensile strain in the concrete, in the pre-stressed concrete bar is 0 prior to the pre-stressing operation, which is the 0, 0 state of the pre-stressed concrete bar. On the pre-stressing of the steel, that is by the virtue of the pre-stressing operation, the concrete in the pre-stressed concrete bar traverses the path highlighted by the green curve, or generally the green straight line path highlighted by the arrow to signify the direction of the stress strain path that is traversed by the concrete in the pre-stressed concrete bar during the pre-stressing operation. As one can note from this graph, the pre-stressing operation changes or moves the state of stress and strain from 0, 0 in the concrete of the pre-stressed concrete bar to a state of stress and strain, or state of strain and stress denoted as epsilon Cp and sigma Cp, since the pre-stressing operation induces the initial compressive strain, or the initial pre-strain epsilon Cp, and a corresponding initial compressive stress or initial pre-stress sigma Cp by the virtue of pre-stressing. And the stress strain path that is traversed by the concrete in the pre-stressed concrete bar is highlighted as the green straight line, or the green curve in general, with the red arrow illustrating the direction of the stress strain path traversed by the concrete in the pre-stressed concrete bar by the virtue of the pre-stressing of steel. that is this concrete in the pre-stressed concrete bar, travels on the stress strain path from the state of 0 stress and strain to the state of pre-stress or the initial pre-compressive stress sigma Cp and the corresponding initial pre-compressive strain or pre-strain epsilon Cp due to the pre-stressing of steel in the pre-stressed concrete bar. Therefore, one can identify that the state of stress and strain in the pre-stressed concrete bar or rather the concrete in the pre-stressed concrete bar is transformed or moved by the virtue of the pre-stressing operation from the state of 0 stress and 0 strain to a state or a stage that will be termed as stage 1 of the stress strain state, that is induced in the concrete, in the pre-stressed concrete bar after the completion of the pre-stressing operation, that is by the virtue of pre-stressing. Therefore, proceeding to the state of stress and strain induced in the concrete of the pre-stressed concrete bar at the end of the pre-stressing operation, illustrated by the green line or the green curve in general. With the red arrow highlighting the direction in which the stress strain path is traversed by the concrete on the pre-stressed concrete bar during the pre-stressing operation. The state of stress and strain in the concrete of the pre-stressed concrete bar after the completion of the pre-stressing operation is highlighted by this green dot and identified by the strain and stress in the concrete of the pre-stressed concrete bar by the virtue of the pre-stress after the completion of the pre-stressing operation, also termed as the initial pre-compressive strain epsilon Cp, or simply the pre-strain epsilon Cp, and the initial compressive stress sigma Cp, or simply the initial pre-stress sigma Cp. Since equilibrium considerations require that the statical equilibrium of each and every cross section in the pre-stressed concrete bar should be satisfied, self-equilibrating internal stresses are generated in the concrete as well as steel by the virtue of the pre-stressing operation. And these self-equilibrating stresses that are typically compressive in the concrete, in this case the internal pre-compressive stress or the internal pre-stress generated in the concrete at the end of the pre-stressing operation is minus 5 MPa with the minus sign representing the compressive nature of the pre-stress sigma Cp while the internal self-equilibrating stress in the steel are generally tensile in nature, by the virtue of the pre-stressing operation, that is, tensioning the pre-stressing steel against the concrete. Hence, the self-equilibrating stresses that are compressive in case of concrete and tensile in case of steel in the pre-stressed concrete bar can be calculated by examining the statical equilibrium of any cross-section of the pre-stressed concrete bar. And considering the force equilibrium along the direction of the externally applied tensile force or the direction of the pre-stressing bar, the internal tensile stress that is generated in the pre-stressing steel can be related to the internal compressive stress induced in the concrete in the pre-stressing bar by this relationship. Since statical equilibrium of any cross-section of the pre-stressed concrete bar requires that the internal compressive force in the concrete that is the internal compressive force resultant of the initial pre-compressive stress or the pre-stress in the concrete of the pre-stressed concrete bar should be balanced and therefore equal and opposite to the internal tensile force, that is the internal tensile force resultant of the tensile stress in the pre-stressing steel by virtue of the pre-stressing after the completion of the pre-stressing operation. And the statical force equilibrium equation representing the force equilibrium between the internal compressive force resultant of concrete in the pre-stressed concrete bar and the internal tensile force resultant in the steel or the pre-stressing steel of the pre-stressed concrete bar may be expressed by this relationship in terms of the steel area ratio. Based on the fundamental force equilibrium equation. Expressing the statical equilibrium between the internal compressive force resultant in the concrete due to the initial pre-compressive stress or initial pre-stress induced by the pre-stressing operation and the internal tensile force resultant in the pre-stressing steel due to the pre-stressing of the steel. Rearranging the terms in the statical force equilibrium equation, noting that the ratio of the area of pre-stressing steel to the ratio of the gross concrete section is defined as the steel area ratio and denoted as rho, given as .0004 as the design data in the question statement of the illustrative numerical example presented in the previous slide, one can relate the pre-stress in the pre-stressing steel, denoted as sigma SP, to the initial precompressive stress or initial pre-stress in the concrete of the pre-stressed concrete bar, where the pre-stress in the steel is tensile in nature by virtue of the pre-stressing operation, while the initial pre-stress sigma Cp is compressive in nature. Hence, substituting the value of the steel area ratio for the pre-stressing steel in the pre-stressed concrete bar, denoted as rho and given as 0.004 as the design data, the initial tensile pre-stress sigma Sp in the pre-stressing steel of the pre-stressed concrete bar can be related to the initial compressive or pre-compressive stress, that is the initial compressive pre-stress sigma Cp in the concrete of the pre-stressed concrete bar, by this equation. That is, the internal pre-tensile stress in the pre-stressing steel induced by the pre-stressing operation sigma Sp is equal to the initial pre-compressive stress sigma Cp in the concrete of the pre-stressed concrete bar, also termed as the pre-stress in concrete, times 1 minus rho divided by rho, where rho is the pre-stressing steel area ratio provided as 0.004 in the design data, thus resulting in the relationship between the initial pre-tensile stress in the pre-stressing steel after the pre-stressing operation sigma Sp is equal to five MPa, that is the desired or design value of the initial pre-compressive stress or the initial pre-stress that is required to be induced in the concrete of the pre-stressed concrete bar to ensure that concrete remains uncracked in the specified working stress range, times 0.996, that is 1 minus 0.004, divided by 0.004, which is the pre-stressing steel area ratio. specified as the design data, thus resulting in a value of 1246 MPa. That is 1246 MPa for the internal pretensile stress, or simply the internal tensile pre-stress that needs to be induced in the pre-stressing steel by virtue of the pre-stressing operation in order to ensure that the concrete in the pre-stressed concrete bar remains uncracked on the application of the externally applied tensile force in the specified range of working stresses under working loads or service loads. That is a stage subsequent or following stage 1, which we will discuss as the next stage in the exercise of tracing and defining the stress strain path of the concrete in the pre-stressed concrete bar or in general the uniaxial stress strain behavior of the pre-stressed concrete bar after the completion of the pre-stressing operation. However, as far as stage 1, that is at the end of the completion of the pre-stressing operation, is concerned, the internal pretensile stress in the pre-stressing steel, also termed as the tensile pre-stress in the pre-stressing steel that is induced by the pre-stressing operation is obtained as 1246 MPa, that is 1246 MPa, based on consideration of statical equilibrium of a general cross-section of the pre-stressed concrete bar at the end of the pre-stressing operation, which one can easily verify corresponds to an internal pretensile strain, or simply tensile pre-strain, denoted as epsilon Cp, where the notation epsilon signifies strain while the subscript S and P denote steel and pre-stress respectively, or pre-stressing steel. Is simply equal to the tensile pre-stress sigma Sp divided by the modulus of elasticity of steel, or the Young's modulus of steel, thus computed as 1246 MPa divided by 2 into 10 to the power 5 MPa, resulting in a value of 0.00623. And since the pre-stress or the internal stress in the pre-stressing steel is tensile in nature by the virtue of the pre-stressing operation. Both sigma sp and epsilon sp are positive, since our sign convention is that tensile stresses and forces are positive, while compressive stresses and strains are negative. Continuing our exercise for the solution of the illustrative numerical example, for which the question statement was presented in a previous slide, that is referred to as the solved example in the current slide, we will begin our discussion by first summarizing the state of uniaxial average applied axial stress and the corresponding average applied axial strain in the concrete of the pre-stressed concrete bar, as well as the pre-stress in the pre-stressing steel bar and the corresponding pre-strain in the pre-stressing steel bar that are required to ensure that the concrete in the pre-stressed concrete bar remains uncracked in the range of working stresses under the working loads or service loads specified in the question statement of the solved example as 0 to 7 MPa. And based on the results of the design calculations presented in the previous slide, one can summarize that the average applied axial compressive stress in the concrete of the pre-stressed concrete bar was calculated as minus 5 MPa as explained in the previous slide, corresponding to the average applied axial compressive strain equal to minus 0.0005, that is minus 0.05%. It is worthwhile to mention here that the average applied axial compressive stress of 5 MPa, or rather minus 5 MPa, where the minus sign signifies compressive stress, and the corresponding average applied axial compressive strain of minus 0.0005 or minus 0.05% are defined or termed as the pre-stress or the pre-compressive stress and the pre-strain or the pre-compressive strain respectively, that are required to be induced in the concrete of the pre-stressed concrete bar after the pre-stressing operation, that is, at the end of the pre-stressing operation, by virtue of the pre-stressing steel, in order to ensure that the concrete of the pre-stressed concrete bar remains uncracked in the specified range of working stresses under working loads or service loads. Given as 0 to 7 MPa. Upon the application of the externally applied tensile force. While the pre-compressive stress or the pre-stress in the concrete induced by the pre-stressing operation and the corresponding pre-compressive strain or pre-strain in the concrete of the pre-stressed concrete bar at the end of the pre-stressing operation, calculated in the previous slide as minus 5 MPa and minus 0.0005 or minus 0.05% respectively, summarize the state of average applied axial stress in the concrete of the pre-stressed concrete bar and the average applied axial compressive strain in the concrete of the pre-stressed concrete bar respectively, for sake of completeness, in the discussion on tracing and locating the stress strain path of the concrete, in the pre-stressed concrete bar, one may note that the axial compressive stress and the axial compressive strain in the concrete in general can increase to much higher values. Since the average applied axial compressive stress in concrete in general as a material can be increased or enhanced to the maximum axial applied compressive stress that concrete can sustain or resist as a material, defined as the characteristic compressive strength of concrete, which in this case is 40 MPa, corresponding to the grade of concrete of the pre-stressed concrete bar selected as M40 grade. Therefore, the uniaxial stress strain response of the concrete, for sake of completeness, may be noted to continue in compression until the peak compressive stress, that is the characteristic compressive strength of concrete denoted as sigma Ck and specified as 40 MPa for M40 grade of concrete is reached, beyond which the concrete will fail in compression, and the average applied compressive axial stress that is resisted by the concrete will begin to decline as depicted in this fragment of the stress strain path traversed by concrete as a material in general under increasing values of the average applied axial compressive stress. It may be pertinent to mention here that the fragment of the uniaxial compressive stress strain path of the concrete displayed in this remaining part of the graph from the previous slide is not really of much significance in the context of the need or the idea of pre-stressed concrete. However, for sake of completeness, the fragment of the uniaxial compressive stress strain path up to the peak compressive stress or the characteristic compressive strength of concrete has been included in the present slide in order to illustrate the complete uniaxial compressive stress strain behavior of concrete as a material in general. More importantly, from the point of view of the need and the idea of pre-stressed concrete, illustrated by the solved example in the present slide, is the uniaxial average applied compressive stress in the concrete and the corresponding uniaxial average applied tensile strain in the concrete, termed as pre-stress or the pre-compressive stress in the concrete and the pre-strain or the pre-compressive strain in the concrete, respectively, that are induced by the pre-stressing operation. That were determined as minus 5 MPa and minus 0.0005 or minus 0.05% in the previous slide. which are the required pre-compressive stress or pre-stress and the pre-compressive strain or pre-strain in the concrete of the pre-stressed concrete bar, that will ensure that the concrete in the pre-stressed concrete bar remains uncracked in the specified range of working stresses under working loads or service loads given as 0 to 7 MPa in the question statement of the solved exam. Further, of significance or relevance from the point of view of the fundamentals and the basic concept or need and idea of pre-stressed concrete are the pre-stress, that is the initial tensile stress in the pre-stressing steel denoted as sigma SP and the corresponding pre-strain or the initial tensile strain in the pre-stressing steel denoted as epsilon SP. That need to be induced by the virtue of the pre-stressing operation in the pre-stressing steel in order to achieve the condition of uncracked concrete in the specified working stress range of 0 to 7 MPa, and as calculated in the previous slide, the pre-stress in the steel, that is the tensile stress, induced in the steel after the pre-stressing operation denoted as sigma SP was found to be 1246 MPa, that is 1246 MPa, corresponding to the pre-strain in the steel or the tensile stress strain in the pre-stressing steel at the end of the pre-stressing operation denoted as epsilon SP. That was found to be 6.23 into 10 to the power minus 3 or 0 or 0.00623. Since our sign convention is based on tensile forces, tensile stresses, and tensile strains, considered as positive forces or positive stresses or positive strains respectively, the calculated values of the pre-stress in the pre-stressing steel and the corresponding pre-strain in the pre-stressing steel are both positive, as the pre-stress in the steel and the corresponding pre-strain in the pre-stressing steel are tensile in nature. Hence, we can now proceed to the next stage, that is the stage 2 in the exercise of tracing and defining the uniaxial stress-strain path or the uniaxial stress-strain response of the concrete as well as the steel, that is the pre-stressing steel in the pre-stressed concrete bar, it may be mentioned here that the stage 2 in the uniaxial stress-strain response of concrete as well as the pre-stressing steel in the pre-stressed concrete bar is reached or achieved upon the application of the external tensile force or the externally applied tensile force denoted as capital T at the cracking of concrete. Recall that the graph displayed in the previous slide depicting the uniaxial stress-strain response of the concrete in the pre-stressed concrete bar illustrates that the stress-strain path that is traversed by the concrete in the pre-stressed concrete bar upon the application of the externally applied tensile force T, as the externally applied tensile force T increases from 0 to the value that is required for cracking of concrete in the pre-stressed concrete bar, denoted as capital T subscript Cr, where the notation capital T signifies the average applied external tensile force T, while the subscript Cr signifies that the externally applied tensile force T is the value of the external tensile load upon the cracking of concrete. Referring to the graph of the uniaxial stress-strain response of the concrete in the pre-stressed concrete bar, one may note that the stress-strain path traversed by the concrete in the pre-stressed concrete bar upon the application of the externally applied tensile force T up to the point of cracking of concrete is highlighted as the pink arrow. Or the red straight line path starting from the state of the pre-stress and pre-strain in the concrete up to the cracking of concrete as the externally applied tensile force T increases from 0 or the external tensile loading increases from 0 to the cracking load T subscript Cr as highlighted by the pink arrow in the graph for the uniaxial stress-strain response of concrete in the pre-stressed concrete bar displayed on the previous slide. In order to identify and calculate the state of stress and strain in the concrete, as well as the pre-stressing steel in case of the pre-stressed concrete bar, at the point of cracking, due to the application of the externally applied tensile force T, up to the threshold value of the externally applied tensile force T that is required to crack the concrete in the pre-stressed concrete bar, denoted as capital T subscript CR, we need to examine the strain compatibility between the concrete and the steel, and considering the compatibility of strains between the concrete and the pre-stressing steel in the range of the externally applied tensile force from 0 to TCR, the increase in axial strain, denoted as delta epsilon, may be calculated as the tensile force shared by or resisted by the concrete in the pre-stressed concrete bar, and denoted as T subscript C, divided by the product of the modulus of elasticity of concrete, that is the elastic modulus of concrete, denoted as E subscript C, times the gross area of concrete minus the area of the pre-stressing steel, which should also be equal to the increase in axial strain, delta epsilon, in the pre-stressing steel. Upon the application of the externally applied tensile force in the range of 0 to the cracking tensile force TCR, and the increase in the axial strain in the concrete therefore being equal to the increase in the axial strain in the steel, by virtue of compatibility of strains between the concrete and the pre-stressing steel in the range of the externally applied tensile force T from 0 to the cracking tensile force TCR, that is prior to cracking of concrete or up to the point of cracking of concrete, the increase in the axial strain delta epsilon in the pre-stressing steel, calculated as the ratio of the tensile force resisted by the pre-stressing steel or shared by the pre-stressing steel, denoted as T subscript S, divided by the modulus of elasticity of steel, E subscript S, times the area of the pre-stressing steel, A subscript S, should equal the increase in the average axial strain in the surrounding concrete, where one may note that the total externally applied tensile force T is the sum of the share of the externally applied tensile force resisted by the concrete, denoted as T subscript C, plus the share of the externally applied tensile force T subscript S resisted by the pre-stressing steel in the pre-stressed concrete bar. Rearranging the terms in the equations numbered as A, and noting that the ratio of the moduli of elasticity of steel to concrete is M, that is defined as the modular ratio M, while the ratio of the area of pre-stressing steel to the gross area of concrete in the pre-stressed concrete bar is defined as the steel area ratio, denoted as rho, as explained in the previous slide. One can relate the share of the externally applied tensile force T resisted by the concrete, denoted as T subscript C, to the externally applied tensile force shared by the pre-stressing steel in the pre-stressed concrete bar in terms of the modular ratio M and the steel area ratio rho, by the relationship expressed in this equation, substituting the values of the modular ratio M and the steel area ratio rho into the relationship between the share of the externally applied tensile force resisted by the concrete TC, and the share of the externally applied tensile force resisted by the pre-stressing steel TS may be calculated as equation number B. Further, equations A and B can be solved simultaneously. To arrive at a compact or concise relationship between the total externally applied force T with the share of the externally applied tensile force resisted only by the concrete in the pre-stressed concrete bar, that is expressed by equation number C. Further, equations A and C can be applied to evaluate the increase or change in the uniaxial average applied tensile stress in the concrete, denoted as delta sigma subscript C, where delta, the prefix, signifies the change or the increase in the average applied axial stress sigma, while sigma denotes the average applied axial stress in the concrete, and the subscript C signifies the concrete in the pre-stressed concrete bar, can be related to the share of the externally applied tensile force T resisted by concrete, denoted as T subscript C, by substituting the values or the relationships derived in the equations A, B, and C, thus resulting in the relationship between the change or increase in the average applied actual stress in concrete, denoted as delta sigma subscript C, with the externally applied tensile force, capital T. In summary, the increase or change in the average applied actual stress in the concrete of the pre-stressed concrete bar, denoted as delta sigma subscript C, equals 0.929, that is almost 93% or 0.93 of the externally applied tensile force divided by the cross-sectional area of the pre-stressed concrete bar. Defining a parameter that is new to this discussion, termed as the externally applied average tensile stress, and denoted as sigma AV, where the notation sigma signifies stress, while the subscript AV signifies that the stress sigma is the average tensile stress due to the externally applied tensile force T, that may be calculated as the ratio of the externally applied tensile force T to the gross cross-sectional area of the pre-stressed concrete bar, denoted as A subscript C. One can further relate the increase or the change in the average applied tensile or actual stress in the concrete of the pre-stressed concrete bar, denoted as delta sigma C, to the newly defined parameter sigma AV, that is sigma subscript AV, termed as the externally applied average tensile stress in the pre-stressed concrete bar as a whole, or the ratio of the externally applied tensile force capital T to the cross-sectional area of the pre-stressed concrete bar considered as a whole, disregarding the individual components, that is concrete or steel. Furthermore, utilizing the relationships expressed by equations A, B, C, and noting the definition of the parameter sigma AV, that is the externally applied average tensile stress in the pre-stressed concrete bar as a whole, one can also arrive at other useful relationships. For example, the relationship between the change or increase in the average applied tensile axial stress in the steel to the average applied tensile stress in the pre-stressed concrete bar as a whole, as expressed by the equation circumscribed by this green rectangle that expresses the relationship between the increase in the average applied axial tensile stress in the concrete of the pre-stressed concrete bar to the increase in the average applied axial tensile stress in the concrete among all these relationships. That we have derived in the present slide based on the considerations of statical equilibrium and compatibility of strains as expressed by equation A, probably the most useful relationship is that circumscribed in the green rectangle here, that presents the equation expressing the equality or relationship rather between the change or increase in the externally applied average tensile stress of the pre-stressed concrete bar as a whole to the change or increase in the average applied tensile stress in the concrete, in the pre-stressed concrete bar. Referring to this final equation, one may conclude based on the derivation in the present slide that the change or the increase in the average applied tensile stress in the pre-stressed concrete bar as a whole, denoted as delta sigma AV, that is the change in the externally applied average tensile stress of the pre-stressed concrete bar, can be equated to 1.08 times, that is 108% of the change or increase in the average applied tensile stress in the concrete only of the pre-stressed concrete bar. Also, the change or the increase in the average applied axial tensile stress in the pre-stressing steel only equals the modular ratio times the change in the average applied axial tensile stress in concrete only for the pre-stressed concrete bar, as expressed by this equation circumscribed by the green rectangle. The two equations together imply that the change or increase in the average applied axial tensile stress in the pre-stressing steel only is equal to 18.58 times the change or the increase in the externally applied average tensile stress of the pre-stressed concrete bar as a whole, as established from these calculations here. Therefore, the final two equations that are circumscribed by the green rectangles, as well as equation C that is also circumscribed by the green rectangle, are the result or findings based on considerations of statical equilibrium and compatibility of strains for the pre-stressed concrete bar considered in the solved example, subject to an externally applied tensile force increasing from value of 0 to a threshold value that is required to crack the concrete. And in the next slide, we will proceed with the calculation of the state of stress and strain in the concrete of the pre-stressed concrete bar at the stage 2, that is, upon the application of the externally applied tensile force T, at the point of cracking of concrete. Using these three equations that are circumscribed in the green rectangles.